These are the week 5 notes for your test Thursday. Now, this is a funny thing here where, like I said, we always learn about S, P, and D, and F, teachers ignore quite a bit, so that kid isn't getting attention, and then G, orbitals, which are like hypothetical orbitals, not actually something that happens, or it's something hypothetical that maybe can be created later, is dead. In a wheelchair, so I didn't really have a chance. All right, so one thing we're going to get into is shapes of orbitals. Remember, S is circle, P like this, and then D, 1, 2, 3, 4. D does have one other shape, but we're going to ignore that. So my goal here is to show you what these orbitals look like, because you might learn the orbitals, but then you're scared of them. I don't really get the bunny and the basket thing, but maybe you do. All right, so we're going to draw the orbitals. The front number is what shell it's in, and the superscript is how many electrons there are. If you've been doing the ALEKS, you know that. And then I'm going to have you circle the valence electrons, the outermost electrons. This is something new I'm teaching, but it was my goal to show you how all this connects. So I'm going to have you draw one and explain the relevance. So S moves like this, 1s, circle. 2s further away from each other, or further away from the nucleus where the positive charge is, because there's a 2 in front. And then 2p, and since there's 6, we're going to have 3 figure 8s. That's not good because, change the color because it wasn't as 1, 2, 3. And we know that this, so argon has 8 valence electrons. So if we look at this, the 2s and the 3p are the ones that are furthest away, and that's why there's 8 valence electrons. Those in the middle are not valence electrons. So let's practice more. We have copper. Oh boy. Copper has 2 valence electrons. I know that by looking at it right there. We have the normal electron configuration. If we rewrite it with the highest number in front or at the end, then we know that those are the valence electrons. All right, 1s2 circle, 2s2 circle, 2p6, 1, 2, 3, 3 figure 8, 3s2, it's going to be even further away because the front number is, well, 3, which makes it further, and then it's an S, so it's circular. And then 3p6, the front number is the same, so essentially it's very close to so here we go. Then 3d9, so keep in mind here we're switching 3d9, that 3 is in front, so it's equidistant. 1, 2, 3, 4, 4-leaf clover, and then 4s2 right here. Those are the valence electrons. that is 4s2. So the ones in the middle are not valence electrons. And keep in mind, electrons will move in a manner to make them closer to the center of the positive charges, but as far away from each other. So think of this in a 3D manner, and that's how electrons would move, or where you would predict them to be. If you did further research on this, you would predict them to be in that area. So here's bromine. This is my first attempt at getting this, and I don't know. I'll name the attempts. You're not going to get one this hard. Anyways, the top one, I'm going to try to do, or I'll do the top one. It's going to be the same as this, as the rewritten one. We know bromine has 7 valence electrons. If we look right now, those are the valence electrons. Those both start with 4. Therefore, they're in the 4th orbital and the farthest away from the center. All right, 1s2, 2s2, 2p6, 3s2, 3p6. You don't have to draw these perfectly, and I'm not going to give you a hard one. 3d10, clover, 1, 2, 3, 4. And then, I was going to switch it, but anyways, I'll go back to this. 4s2, and then 4p5. 1, 2, 3. And so then we see that the outermost electrons are here, and that there are 7 of them. So that's why that D is a 3. It goes closer to the center based on its movement. Here we're going to learn about quantum numbers, and these are going to take some practice. N is the front number, so if we pick 3d5, 3d6, let's do N is 3. The angular momentum, and this is done because electrons can't exist in the same spot at the same time. So S is 0, P is 1, D is 2, F is 3. The angular momentum is the shape, essentially, and this is D, so that is 2. Now, the magnetic quantum number is a little bit tough, but we'll practice them. Remember, D has 10 electrons. Every orbital can hold 2. So if it's S, we're going to have 1 box. If it's P, we're going to have 3 boxes. And if it's D, we're going to have 5 boxes. Because S is 2 across, P is 6 across, D is 10 across. We have 6 electrons in that D orbital. Electrons want to be as far apart from each other as possible. So we have to put 6 in, up, 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 up. So we're going to start with up. We have 5, down. So this is the electron we care about. We start at 0, minus 1, minus 2, plus 1, plus 2. This electron is in minus 2, so it is negative 2, and it's pointing down, so it's negative 1/2. So the 4 quantum numbers are 3, 2, negative 2, negative 1/2. And we'll do another practice one here. Now if we picked S, so D is the hardest, so I should have maybe started with S. I'll start with the S in the notes. So if we picked 4s1, principal quantum number, how far it is from the center. You know from the last part that the front number determines how far it is. The angular momentum is the shape. Remember, S is 0, L, S, P is 1, D is 2, F is 3. So angular momentum, L is S is 0. S has one box, it has one electron in it, so up, and we're starting with the center, so that's going to be 0. So every quantum number for M of L is going to be, for an S is going to be 0. It's pointing up, so it's positive 1/2. So 4s1 is going to be 4, 0, 0 plus 1/2. Now let's try a p orbital. So if we picked 2p5, which would be fluorine, principal quantum number, distance 2, p is 3 boxes, p is, so s is 0, p is 1, d is 2, f is 3. I won't give you enough. P is 1, magnetic M of L, P has 6 electrons in it, so we have 3 boxes. There's 5, up, 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 down, down. 5, 0, minus 1, minus 2. We're looking at the last electron, so that is 0. Nope, that is, yep, 0. Then it's pointing down, negative 1/2. So we'll do some in class that are different, but the quantum numbers for fluorine, or 2p5, are going to be 2, 1, 0, minus 1/2. We have to know why the elements get smaller as we move across the periodic table. So remember, helium, fluorine are the smallest, francium is the largest, so therefore, as we go across the periodic table, it's going to get smaller. And this has to do with nuclear charge. So as we go across the periodic table, there are more protons in the center. So let's pretend Taylor Swift cloned herself to be at more football games, to make more people mad, and there's more protons in the center because there's more Taylor Swifts performing, or there's more of an attraction between these electrons on the outside and the center. So therefore, as you go across the periodic table, nuclear charge increases and radius decreases. We can look at an ALEX here. We have technetium, which is element 43. However you say that next word, that is element 44. Cadmium, element 48. And then zirconium is element 40. So it says nuclear charge, rank the following of experienced nuclear charge. So I'm assuming that 1 is the highest nuclear charge. I'll have to look on ALEX. But if we know that nuclear charge, as we go across the periodic table, it gets larger. So cadmium is the closest to neon, or to the right, so it's going to be 1. Then ruthenium will be 2, because it's more to the right. Then technetium, 3, and 4. And so those are good to practice. I'll probably ask ALEX. This one here, more practice. And now, elements, as we move down the table, why do they get bigger? Again, I'll make this an ALEX question. And that is because they have more shells. So that also is known as a shielding effect, but I didn't put that in the notes. But essentially, the concert hall gets bigger. Maybe this is Taylor Swift when her first album came out, then her next, or Taylor Swift in the middle, then her third, and then after she released Shake It Off, the concentrates got bigger. There's more thingies. There's like more, the stands are bigger. All right, so protons, this is easy, silicon, top number. Then we have 14 electrons. Carbon, 6 electrons. Lead, Pb, 82 electrons. So we know as we go down, it gets larger. So carbon's going to be the smallest, silicon's going to be next, and then lead, Pb, is going to be the largest. And valence electrons here is the outer electrons. Silicon has 4, carbon has 3. No, silicon, yeah, carbon has 4. And lead has 4 as well. The number of shells is going to be what the highest number is in their electron configuration. So silicon has a 2,3p, so 3 as a 3s and a 3p. Carbon has a 2s and a 2p, and lead has a 2, 3, 4, 5, 6p and a 6s, so that's 6. So this is the largest, then next, then smallest. Again, some more practice on Alex. Now the last number is m of s. That just means we have a positive 1/2 or a negative 1/2. So remember, if the arrow is pointing down, it's negative 1/2. So this would have to be like this. And if it's pointing up, it's a positive 1/2. Well, this is an explanation that I found on Instagram chemistry page. And if that makes sense to you, it doesn't make sense to me, so I don't know. But I do know pointing down is negative 1/2. And so here, if we have a 3p4, 1, 2, 3, up, 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 down, 0, -1, +1, it's pointing down, that's negative 1/2. That is because it's pointing down. And then if we have 3p5, quantum numbers are going to be 3, 1, because p is 1. And then p is 6, 3 has 6, so it has 3 boxes, 0, -1, +1, 1, 2, 3, 4, 5. So it's 0 because it's in this one, and then it's pointing down, so negative 1/2. Do another one, 3p2, 3 boxes, no matter what, even if it's 2, quantum numbers are 3, 1, up, up, 0, -1, +1, then 0, 0, it's up, positive 1/2. So why do we do this, or what connection is there? Now, the electron configurations help determine radius and ionization energy. I should have wrote electron affinity. But one thing, last thing here, is the magnetic properties. If something is paramagnetic, so it's S1 up, it's P3, it's D7, these have unpaired electrons. Therefore, they're more magnetic, or they are magnetic. So para, more magnetic. Now I always forget this because para does sound like 2 and di is a prefix for 2. So It's a little tough, but that is paramagnetic. Diamagnetic is if there are no unpaired electrons. That's going to have to be an S2, P6. So you're always going to draw 3 boxes for P. You're always going to draw 5 boxes for D. So S2 is diamagnetic. D10 diamagnetic because we have 10, and those are non-magnetic. Remember, we go up, up, up. These are plus 1/2, plus 1/2, plus 1/2. And then if it goes down, it's negative 1/2, negative 1/2, negative 1/2. So that is it. One thing I want you to remember though is I took off, the lesson seemed to be getting kind of long, but because of lab this week, you are going to have to know where the metals are, where the nonmetals. Remember, these are the metals, and that's it. There's nothing else. And these are, with hydrogen, the nonmetals. So to the left of the semimetals or metalloids are the metals, and to the right are the nonmetals. And you can go 5, 4, 3, 2, 2, and something to study and be ready for the test Thursday.